In this video, I'll be discussing how to assign oxidation numbers to different elements within a molecule. I'm going to save the processes of oxidation and reduction for when we talk about redox reactions. For right now, I'm just going to focus strictly on how to assign oxidation numbers. So here are the general rules of thumb that you'll use when assigning oxidation numbers to elements. And this is basically what I go by when I go through the process of assigning oxidation numbers. So the first rule here, an element in its natural state is going to have an oxidation number equal to 0. So what do I mean by natural state? Well, an example of this would be solid sodium, NaS, with no charge on it. This would be sodium in its natural state. This would have an oxidation number of 0. Another good example would be diatomic oxygen, O2. This is oxygen in its natural form. Therefore, the oxidation number on this, on the oxygens in here, would be 0, because this is natural state. Monoatomic ions, and that's going to be one atom with a charge. So monoatomic means one atom, ion means charge. Those are going to have oxidation numbers that are equal to the charge on that atom. So this is going to be very prevalent when you have transition metals by themselves. So for example, Fe3+. The oxidation number on this is going to be equal to the charge, which is 3. So the oxidation number would be +3 for this Fe3+. For oxygen, the oxidation number is typically going to be -2, except for when you have oxygen-to-oxygen bonds or oxygen-to-fluorine bonds. But the vast majority of the time, oxygen will have a -2 oxidation number. Hydrogen. Hydrogen is going to most of the time have an oxidation number of +1. However, when hydrogen is bonded with a metal in what's called a hydride, then it's going to have a -1. But the vast majority of the time, hydrogen is going to have a +1 oxidation number. Group 1A is typically going to have an oxidation number of +1, and group 1A is hydrogen going down that first column. So sodium, potassium, they're usually going to have a +1 oxidation number. Group 2A, the same logic applies. Oxidation number is typically going to be +2. For the halogens, the oxidation number is usually -1. So the halogens are the group 7A, fluorine, chlorine, bromine, iodine. Usually they're going to have a -1 oxidation number, but that can change depending on the context. And probably the biggest rule of all that helps us for the elements that we don't know, the overall charge of your molecule is going to be equal to the sum of the oxidation numbers for each element in that molecule. So this right here is something we can use to solve for the elements that we don't know the oxidation number of. And that's what we're going to look at now. We're going to look at some examples of assigning oxidation numbers that we don't know based on our rules up here. So this first example we're going to look at here is this magnesium nitrite molecule. And what I always like to do when I have to assign oxidation numbers, I like to have a running tally of what I know based on the rules. So I just go through and just mark everything based on what I know the oxidation number for. So we'll start with magnesium. So magnesium is a group 2A metal. So it's going to be, based on our rules, +2. It's in group 2A. Okay. Oxygen, well, we don't have any of the exceptions. We don't have an OO bond, we don't have an OF bond. So oxygen is pretty safe to say it's going to be -2. However, how many oxygens do we have in the molecule? So we have 2 in each nitrite, and we have 2 nitrites. So 2 times 2, 4. So you need to multiply that oxidation number by the number of those atoms you have in your molecule. We have 4 oxygens in this molecule, therefore we have to multiply that -2 by 4. So for nitrogen, which is the last element we have in this compound, we don't know. Nitrogen isn't in our rules, and nitrogen is ultimately going to be the one we solve for in this problem. So to solve for it, I'm just going to make it x. And we're going to set up a very simple algebraic equation and solve for x. But how many nitrogens do I have? I have 2. So make sure you put that. We have 2 nitrogens in this compound. So I'm just going to set up a very simple algebraic equation, and we're going to set that equation equal to the charge of the molecule itself, which is neutral because there's no charge here. So we'll set the equation equal to 0 because our compound is neutral. And this is what our algebraic equation will look like. We'll take the 2 from the magnesium minus 8, that's the total of the oxygens, so the -2 times 4, because we have 4 of them. That's where the 8 comes from, minus 8. And then 2x, that's our nitrogen. And we're trying to solve for x, and the x will let us know the oxidation number for nitrogen. So 2 minus 8 is going to be -6 plus 2x equals 0. Add the 6 to the other side, you get 2x is equal to 6. Divide the 2 to the other side, you get x equals plus 3. And this is going to be the oxidation number for nitrogen in this molecule. So nitrogen is going to be +3 for its oxidation number. And that's the same process you'll use to solve for those elements where you don't know. You'll take the elements that you do know, put them into an algebraic equation with x, solve for x, and that will be the oxidation number for your unknown element. So let's look at a slightly more complicated one and do the same approach that we used for the previous one. So I'm just going to look at my elements that I have in my compound to see which ones I know. I have uranium, don't know that one. I've got oxygen, we know oxygen. And we have hydrogen, and we know hydrogen. So I'm just going to take a tally of my elements here. So U is going to equal X, because that's what we're trying to solve for. We want to know the oxidation number of U. And it looks like I have U and then a 2 out here, so I have 2 here, because I have 2 uraniums. Oxygen. So we know oxygen in this case is going to be -2, but how many of them do I have? So I have 4 of them here, and I have 4 of them here. So 2 times 2 is 4 right here, and then oxygen right here times 4, so that's a total of 8. Okay. And then hydrogen. Hydrogen we know is going to be +1. But how many of them do I have? So hydrogen is here in this hydroxide, and times 4, so there's 4 hydrogens. So now we can set up our algebraic equation. The overall charge is 0, so that's what we're going to set our equation equal to. So we have 2x for the uranium, minus 2 times 8, minus 16 for the oxygens, and +1 times 4 is just +4 for the hydrogens. We'll set this equal to 0. So -16 plus 4 is -12. So 2x minus 12 equals 0. Add the 12 to the other side. 2x equals, oops, getting a little ahead of myself. 2x equals 12. Divide the 2 to the other side. X equals 6. Positive 6. So that is the oxidation number for uranium. And it's that simple. You stick it in an algebraic equation and solve for X based on the other elements that you know in the molecule. So uranium in this case would have an oxidation number of plus 6. So how about for this guy right here? So this guy is going to be one of our exceptions, and that's the reason I wanted to point it out. Lithium hydride. So lithium is a metal, and we've got hydrogen bonded to a metal. So the lithium is in group 1A, so we know it's going to be +1, group 1 metal. And hydrogen in this case is bonded to a metal, so the hydrogen is going to be -1 for the oxidation number. So that's a good example of one of your exceptions to your rules. So we'll look at one more example here. So we've got the phosphate ion, PO4 3-. So we're solving for phosphorus, so we're going to make P equal to X. And oxygen is going to be -2, and we have 4 of them. Like that. For a total of -8. And you'll notice that the overall charge in this case isn't neutral, it's -3. So in this case, we'll set our equation equal to -3. Sorry about that, my clock was going off. Sorry if you could hear that. Anyway, what I was just saying was the charge in this case is -3, so that's what we'll set our equation equal to. So set it up like that, and make sure you set it equal to -3, which is our overall charge. And you can probably just do this in your head, right? Add 8 to the other side. X is equal to +5. So +5 is going to be the oxidation number on phosphorus. So that's how you go about assigning oxidation numbers. You use your rules of thumb for the elements that you do know, particularly like oxygen, hydrogen, the groups 1 and 2 metals, monoatomic ions if you have them, halogens, and then you can use simple algebraic equations to solve for the elements that you don't know. You just set them up in your equation, set it equal to the overall charge, solve for X.